So, let us look at the distortion. Right. So, what is this distortion? This distortion comes about because of which terms are non-zero. This distortion comes about because now phi 2 is not 0, non-zero or non-negligible in terms of negligible. Okay, fair enough. So is phi 1, so is phi naught. So, a typical pulse, now I am sketched an electric field also in addition to the envelope, I should say, over here, where if you see it is not, it need not be in this case that in all cases that the envelope also suffers a distortion. It is enough if the carrier suffers a distortion. In other words, in the case where phi 0 and phi 1 were non-zero, but phi 2 and greater were 0, which was the previous case. Compare the notions of this here, that the spectral phase here was flat in both these cases across all frequencies. Phi 1 was the spectral phase was, sorry, the temporal phase, not the spectral phase. The temporal phase was flat in both these cases, where phi 1 of the spectral domain was 0 and the phi 1 of the spectral domain was phi 1 of spectral domain, that is group delay was minus 20 femtoseconds. The temporal phase was flat, whereas the spectral phase in this case, in the two cases which we compared, was linear in both cases, whereas it was constant in the case where phi 1 was 0, it had a negative slope of minus 20 femtoseconds in the second case. But in the time domain it turned out to be that the temporal phase was flat. Agreed? Are you with me? Ergo, what did this mean for us? This essentially meant that of course, we should be really careful in noting down the domains in which we are discussing. All this discussion about phi 2, phi 1 being non-zero is in the omega domain. So, in this case, in the time domain, this also meant that omega instantaneous was omega naught minus d phi by dt, which was 0. The carrier frequency remained constant in time. Instantaneous we did not call it instantaneous carrier frequency, but that is what we meant. In this case, the instantaneous angular frequency we called it, but shorten it to instantaneous frequency was constant in time if phi 2 of omega was 0. So, if I can call upon once again my graphical skills. Okay, I am drawing far too few cycles by doing that. Okay, I have essentially sketched for you again a fairly few cycle pulse, but makes the point that nu or omega instantaneous is forever nu naught. Whereas here you see nu instantaneous on the left to nu instantaneous on the right of this scale. If I can make this, call this my 0, left and right mark with respect to this 0 of my time axis. So, the frequency here is lesser than on this side. The frequency is instantaneous frequency, nu instantaneous increases with time. We have not done any math. If you take my word for it that that this figure is correct, the second order phase, if the up to the second order phase, the in the spectral phase expansion we have non-zero terms in the Taylor series, but third order onwards is 0, phi naught is non-zero, but phi 3 and others are 0. To keep the discussion more accurate, phi 3, 4, 5 are 0. Then this depiction is accurate, and it would tell us that now the instantaneous frequency varies linearly in time. And this is one case where the instantaneous frequency increases with the increasing direction of the time axis, which the way we sketch is left to right. There is nothing preventing us from considering a scenario in which the instantaneous frequency falls with time. Now, it's just as natural, if you wish, that both these can happen, that any of these can happen. So, in either case, the linear variation of the instantaneous frequency with time is called chirping, and a pulse where this happens, which invariably happens to most laboratory produced pulses, these pulses are chirped. Why chirp? Why the adjective chirp? Because this is very natural, nature does it always. Our voices also correspondingly are producing frequencies which are varying in time. Music has this written all over it, or whatever, all signals have this. A color on the wall, if you wish, okay, it's static in time, but if I have sweep the color across the wall, it varies and it's not constant. So, it's really very natural. Maybe this green screen behind me is the flat phase type of scenario, which is somewhat boring, but it's useful for editing out stuff in a video apparently. So it's used in a very modest NPTEL video and in great movies with lot of animation, right. Okay, so that's the phenomenon of chirping of a pulse. Chirping therefore needs to also be quantified and qualified, so that we, in this case, the variation of instantaneous frequency owing to chirping is linear. This is related to a non-zero second order phase. So, if the second order spectral phase is non-zero, whereas the higher orders are 0 or negligible, in the time domain the instantaneous frequency varies linearly in time and the pulses are said to be linearly chirped. Now, without further ado, we can make one more leap forward and anticipate that if the third order spectral phase term was non-zero, phi 3 of omega was non-zero. Phi 3 is not of omega, phi 3 in the spectral domain, because if phi 3 of omega depends on frequency, then that means phi 4 of omega, phi 4 is the next higher order Taylor coefficient is non-zero. So, if phi 3 is non-zero in the spectral domain, then we would anticipate that even the chirp is not linear anymore. It is a statement in anticipation pending proofs which we can figure out. It is just a game of Fourier transformations. Yeah, it is just a game of Fourier transformations which one can do very well numerically, right. So, that is the second order chirp. So, let second order phase, non-zero phase or linear chirp. This is very good and very important in femtosecond science. Why? Because of two reasons. One is what was the adage? If you made it, you should be able to measure it. You made it only if you measured it, right. So, if we want to claim that we made it, or maybe you can say you found it, that is because you measured it. So, this is measurable, but how? This brings me to the next puzzle for you in this course. This is an easier puzzle, possibly or relatively, not really easy. Someone obviously was at a peak of at least was very creative in deducing methods to measure this. So, there are methods to measure it. So, this is probably a more measurable thingy than the phi naught itself, though I have indicated clues from my just prior knowledge, not out of my creativity or imagination on how to measure phi naught or get a measure of phi naught. Here, how the linear chirp is measured is another point for us to think about, right. Once again, not obvious, yet a good puzzle to tease oneself with or spend some happy minutes or hours trying to figure out a good method to do this. But then let us quantify all this and write this down in a neat expression, having understood that the quadratic term in the spectral phase function, which is phi naught plus phi 1 omega plus phi 2 by 2 factorial omega square plus 0 for the higher order terms. For this scenario, okay, this 2 factorial, which is 2, sometimes can get absorbed into the phi 2 term. Phi 2 is a constant for a medium. This is group delay, which has units of second of femtosecond, whereas this is group delay dispersion, the dispersion of group delay, which has units of okay, it's all the radians go away. So, this should be in units of square of time, because there is radians on the left and the right. So, this should have units of inverse of frequency, right. So, this would be okay. Let me not get ahead of myself. I will figure out the units for this and let you know subsequently. So, this is group delay dispersion. The dispersion of group delay is non-zero. So, if I have up to this, then it translates to this expression for a linearly chirped Gaussian pulse, where the amplitude being Gaussian is a matter of choice. We chose it. Let us choose one of our favorite functions, because we know how to do these Fourier transforms very well. That is the whole idea. And this is a product of two functions whose Fourier transforms we want to determine analytically. In this case, the group delay dispersion being non-zero leads to the frequency domain description. In the frequency domain, or rather in the time domain description, beta being non-zero. Okay. So, this parameter is beta is the parameter that concerns itself with the chirp of the pulse, whereas the alpha, if you wish, if had it been just a Taylor expansion thing, alpha, if you wish, is nothing but omega. So, alpha t plus beta t square in the Taylor sense essentially is the first order Taylor term is the carrier frequency, whereas the second order is the chirp. Beta can be positive or negative. Okay. So, the fact also remains that when for t, what is t? That is a good question to ask ourselves. What do I write t here to be? Where do I place the 0 of time? Yeah, this is a good question, I must ask you. Where is the 0 on the time axis? And that is because? Gaussian, but I could have placed it as, I mean, why do I mean, does time go negative in any clock? No. So, I would, what if I placed it at the tail? I mean, so Ritesh wants to educate us that the time that you are having here is this, what we write as t here is some t prime minus z by some what velocity is, okay, he calls it Vg group velocity, which we have we introduced group velocity formally yet? Let me think about it, but since Ritesh called it Vg, we will call it Vg, or we could have called it V Ritesh also, would be just as fine, but it is a good measure of the velocity of this, something that connotes the pulse, right. We will have to formally define that. So, he says that because you made this transformation, therefore, you are having this here, but why did we make this transformation, or where is that imprinted on this, in this discussion? Okay, the fact remains that if this is a travelling wave, it should have had the form, should have had some x minus Vt somewhere, right. And what is the V here? It is Ritesh's Vg for this pulse, a group velocity. Okay, the obvious need for group velocity arises from the following fact, that here it is not a monochromatic frequency which is propagating or moving. For a single frequency wave, we had a neat definition for velocity. It is the speed with which a point of constant phase moved across space time. We call this the phase velocity, and there was only one frequency. Now, here there are a group of frequencies centered about omega naught or nu naught, right, and they all are moving with their, you can say, individual phase velocities which are a function of omega, because v phase is the in vacuo speed of light divided by the refractive index, which is a function of omega. This would be the phase velocity of these individual frequencies in a material medium. Had it been vacuum, there would not be any need for discussing any of these aspects. Either the pulse is propagating in a medium, or it had propagated some time back in such a medium and emerged out, and I am talking about such a pulse, which is why it has a chirp, right. It is a characteristic of the pulse, but the dispersion of the medium has given the phase velocities different numbers, so to say, but this is no more a good measure of the velocity with which the entire group of waves, which we call the pulse, moves. Therefore, I must define for the entire group or packet of waves, it is a packet of frequencies or waves, the velocity with which you can say the energy is being transported. Okay. There is a lot more to group velocity than and phase velocity than this. For example, things like, what is carrying, at what speed is information being carried, because pulses carry information in optical fibers. Should I associate the phase velocity with information or group velocity? Good question. Can group velocity be faster than the in vacuo speed of light? The question. Or what about phase velocity? Can it be faster than the speed of light in a medium and stuff like that? This has given rise to concepts like superluminal propagation of light and fascinating optical scenarios, which we are not going to discuss in any detail over here, but there is something in terms of the physics of group versus phase velocities. But what he says is that we are now using a scaled or a Lorentz transformed, if you wish, time variable, which is t prime is t is t prime minus z by Vg, or t prime is t plus, okay, it's trivial. I will not even bother writing it down, right. Okay, so the point is, this is correct. So we are using a frame of reference which is moving with respect to the pulse, okay, which is appropriate because there is no x minus Vt form here, right. Therefore, this equation here, E of t is equal to whatever is on the right, is not necessarily a propagating pulse. It is just a time domain description of whatever is happening. It could well be happening at a point, say x naught somewhere. So, we threw away that aspect, right. If I set x is equal to x naught and threw away any spatial dependence, so that I focus only on the time dependence, then this phenomenon should freeze in time, so to say, but I can't freeze the pulse in time and still talk about its propagation and dynamical behavior. My other option is to run with respect to the pulse, okay, in a frame of reference, where if this is t prime, the pulse moved, so to say, the pulse is a moving phenomenon. So, in the t prime frame, the 0 of time axis is somewhere, and we captured a snapshot of the pulse at some instant, and that is described by the equation which is written here. But I can also have adopted a co-moving frame with the pulse where this is the 0 of my time axis, and the entire frame of reference is moving with respect to the pulse, such that the maximum is always referenced to 0 in time. Okay. Now, this definition of t brings about a nuance in terms of the way in which we must think of these chirped pulses, in the sense that when beta is positive, which is one of the two cases, then what happens? Omega naught is a fixed term, it is a fixed number for this pulse. Now, think of the second term here, it is trivial, but think of this second term as beta t times t, factor out the t. So, it is omega naught plus beta t is the instantaneous frequency. But t takes values lesser and greater than 0 in this description. Therefore, on one side of the maximum of the pulse, which we have referenced to as 0, we would have lower instantaneous frequencies, that is what we call the left side versus the right side, where the instantaneous frequency is higher than the what we may call the original instantaneous frequency, or the carrier frequency, original carrier frequency, which probably is something about a cycle of the wave from, a cycle of the wave from here to here. When it finished one cycle, somewhere close to the 0 of time we would have had, if you measured an instantaneous frequency there, it would be closest to omega naught, or the carrier frequency, right. So, this also sets us with the fact that carrier frequency now is notional, right. Your frequency is being swept, the center of that distribution wherever is the carrier frequency. It may not even in some sense that way exist as in written on stone or whatever, it is a concept that we use, and frequencies can vary in time. So, that is a linearly chirped Gaussian pulse, right. So, we can therefore now consider, in fact, I made a slight mathematical error here, in that I should have taken the derivative here, right. So, it should have been, we should be careful of these factors of 2 here. Omega instantaneous would be, because of the derivative, twice beta times t. So, the instantaneous frequency versus time for a chirped pulse is essentially omega instantaneous of t plus twice beta. So, beta can be both greater than 0 as well as lesser than 0, but not at the same time for the same pulse in a given medium, depending on the optical characteristics of the medium. So, what optical characteristic is it which determines whether beta is greater or lesser than 0? What characteristic is it? Can you guess that? Not guess, can you deduce that? Oh, you know everything. Yeah, sure. So, but then that is a terminology, but for an audience uninitiated, this sign, owing to a previous discussion where we linked phi 1 to n and n of omega, and we linked phi 2 or rather to an n, and here we link to the frequency dependence of refractive index. So, we could have had two scenarios where dn by d omega, the slope is greater than 0, or dn by d omega is lesser than 0. We would have had two scenarios for the derivative, which would correspond to beta being either positive or negative for a pulse that started as say an ideal say pulse and entered into a medium with either positive or negative dn by d omega and propagated through it. So, he said which is normal and which is anomalous, dn by d omega greater than 0, is it normal or this is normal, this is called normal. This is anomalously dispersive. So, all media are identically normal and anomalous at the same time, depending on which set of frequencies we are concerning ourselves with. And I will close today's discussion with the following. Owing to the simple fact that refractive indices and absorption coefficients, corresponding absorption coefficients, which we can call the n and the k for these media. This is refractive index and this is absorption coefficient for that medium, have this very nice relationship. Okay, if the absorption for a medium, absorption has to be okay depending on how you describe it, but in this case it can only hold one sign, has to be, I mean if there is if this has both signs, one would be absorption, the other would be emission, which normally media without pumping and stuff shouldn't engage themselves in, would be a gross violation. But then we would then have that n of omega and k of omega share this intimate relationship about the special frequency, resonance frequency. A resonance at absorption maximum connotes some kind of resonance in the interaction between the electromagnetic wave and the medium. The wave gets very efficiently absorbed there. So, on either side of the resonance, the behavior of the okay, now I am a bit lost as to where I was. There I was. We will surely close with this. Here you see the refractive index is increasing with frequency. Here it is decreasing with frequency. and we have these to be normally dispersive, the dispersion or the variation of the index width I hope I spell anomalous correctly, or I don't. I hope there's no anomaly in my spelling anomalous if you wish, but please correct me if I'm wrong. So yeah, that's the whole point, and this is an easier word to spell. I hope I got the anomaly right. Okay, so much for spelling bee. So that's the whole reason why we have these dependencies, and often some of this is expressed in the way in which we are taught to express dispersion as stuff like this. As this is why maybe in elementary or early considerations in optics we would have expanded refractive index dependence in wavelength to be in inverse powers of wavelength. But all this comes about because of a harmonic oscillator like model for the atom, which is true both classically and quantum mechanically, the picture. Okay. So, media are anomalous and can have anomalous and normal dispersion. So, if you want to, I will close with this, if we want to manage pulses and pulse shapes, this has an immediate consequence in communication, in optical fiber communication. After all, at the end of the day, it is optical fibers which bring data, even if we have satellites and whatever, right. So, even now it's they literally have sneaked into homes, rooms, and wherever they primarily the last mile or the last meter delivery is done by optical fibers, whatever the G in the spectral band, right, finally, and then the Wi-Fi again throws it out over a few meters at best, it dies down, right, can't even cover few room apartment, but then that is the magic of optical fibers, in which case the point being that we must be able to manage the distortions in these pulses, as you evidently would hopefully agree that if pulses start getting distorted too much, the information they carry can get garbled. So, we must manage dispersion, for which both normal and anomalous are important. Normal dispersion exists in the fiber as pulses propagate through, and they essentially start stretching in time, however so gradually, and will eventually lose information integrity. So, every so many meters or whatever, you want to compensate the dispersion by switching from a normally dispersive fiber to an anomalously dispersive fiber or a dispersion compensating fiber. So, if the pulse got broadened due to normal dispersion, you use dispersion compensating fibers which would compensate and restore this balance. So, the beta would have switched in terms of the chirp. It is not only dispersion due to chirp, but also however so small in a fiber, it is also nonlinearity which can optical nonlinearity which can play a role in the whole business in the whole gamut of things, because, and again I leave this for you to consider as a puzzle or as food for thought. If n as a function of refractive index was not constant as a function of intensity, it was n naught plus an n2i, the first non-zero term in this nonlinear consideration. What we did was a nonlinear consideration of phases in time. So, now ergo also refractive indices. Now, we consider nonlinear Taylor expansions in intensity. Now, understand that I for a pulse is inherently a function of time. So, there sneaks in n as a function of t being something within the pulse, and n being dependent on t within the pulse. Think Fourier is n depending on omega. It is another source of dispersion. owing to the intensity dependence of refractive index, which we normally ignore for window glass, does not matter. But if you have kilometers of fiber, even if N2 was tiny, now this accumulates as a function of length, kilometers of length. How many wavelengths? What is the scale for length there? The unit is a wavelength. Take a kilometer, how many wavelengths is the pulse propagating, right? So it accumulates, it has that much opportunity to accumulate something dispersive, and hence even a small amount of nonlinearity can wreak havoc in your system. Ergo, compensating dispersion is again of paramount importance in optical fiber communication systems. Okay, so that has got everything to do with chirp, but the take home message finally, and I said finally many times in this lecture, this is truly finally, is the following fact, that it is the ease with which you can compensate that matters. And we love linear chirp, and we probably do not do so much for higher orders because we can manage linear chirp. It is a small perturbation, it is a manageable perturbation to the system, whereas higher order chirps may not be. And we will see later that life gets really complicated in trying to manage quadratic and not linear chirp. Okay. So, with that we will pause here for today. I think we have had some discussions. So, I will leave any questions and the such for the next lecture. Thank you.